so these are the notes we wrote last time, and I will put this up on Schoology when we're finished for today, so you don't have to try to copy down everything that we talked about at the beginning of class when some of you were at the Virginia Tech meeting. But we introduced the idea of an average rate of change, and an average rate of change was an algebra slope, the slope between 2 points. And we practiced that on the front here, and when you look at this later on and kind of take your time to look through it, if you weren't here when we worked it out, you'll see we took 2 x's, we used the function to find the 2 y's that went with those x's, and then found the slope, change in y compared to change in x. y2 minus y1, x2 minus x1. Same thing with a set of data. Then we went through the whole big thing about instantaneous rate of change, or derivative, or slope of a tangent line, that we wanted to be able to calculate. That calculus was created around, one of the ideas was to find rate of change at a single point, slope at a single point. And we went through the whole blah blah big thing to basically come up with the fact that this particular limit formula was going to give us the ability to calculate this thing called a derivative, or an instantaneous rate of change, or the slope of a function at a single point. IROC, abbreviation for instantaneous rate of change, just a synonym phrase for derivative. Slope of at a single point. We will sometimes call that I can add another phrase in here. Oops, about, I know. Like, why is that not working? Because I have moved things around since earlier this morning. Okay, derivative, instantaneous rate of change. Why does everybody help? There we go, okay. The slope of what's called the tangent line. Creating a tangent line, or thinking about a tangent line, a line that touches the curve at one point, it's called a tangent line, is going to be important to us. So we will be using all of these phrases: instantaneous rate of change, derivative or derivative value, tangent line slope, to represent doing the exact same thing. So that took us all the way up to here, where I showed you this other version of the limit formula that calculates the derivative. It looks a little different than this one, but it basically has us doing the sort of the same thing, where we have 2 points on a curve. When we move the 2 points closer and closer together, the slope between the 2 points becomes the slope at one point, and taking this slope and then attaching that limit concept to it is making that happen. So we were just about ready to look at how to do this, how to use this formula, this limit formula, to solve a problem or answer a question about finding a derivative. So here we go. So problem 1 says we're going to find the derivative of that function, f of x equals 4x minus 5, and we're going to find the value of the derivative when x equals 2. Okay. And we're going to use a formula for right now that is going to be the limit as x approaches a of f of x minus f of a over x minus a. Now, just like any formula, in order to use a formula, you have to know where to get the stuff to plug into it. So when you're looking at that, you're like, okay, well, what the heck do you mean, like f of x, f of a? You know, where are we getting those things? So that's the first thing we got to talk about. Second thing, because this particular formula happens to also be a limit, we're going to need a little bit of limit skills to use this formula to calculate the derivative. Until we learn another way, which is actually going to be sooner rather than later, but for the next couple classes, we're going to focus on this technique, using this formula to find our derivatives. So the f of x is the function they give us. So in this problem, f of x is 4x minus 5. And here's the little bit part that's a little bit confusing. When we have the a versus the x, a is referring to a specific x value, where x is just always going to still be just an x. So a is in fact the 2. X is just going to be x when we use this formula, always. X will be x. In this particular problem, the a is 2 because a is the specific value of x that we're supposed to use. And so f of a will be f of 2. Which means do what in this problem? How do I find f of 2? What's the formula? Or what's the function? What does the f function say to find f of 2? You're probably right. What does the f function say? Do what with the x? Multiply it by 4 and then subtract 5. I'm just looking at that, right? So f of 2, f of any x value, we use that and we get 3. So I got that. Oops, I'll do that. I guess that's not too bad. All right, I'll move this over a little bit. All right, so we have this that we needed, we have this that we needed, we have that, and we have that. So I'm going to go ahead and just kind of go on another page here. We'll put it on dual so we can look at both. So here's what I'm going to do. I'm going to take my formula, the limit of x approaches a, of f of x minus f of a over x minus a. And I'm going to put the particulars in. The limit as x approaches 2 of 4x minus 5 minus 3 all divided by x minus 2. Okay. If I use my highlighter, that is the f of x part. And I know that because they told me that in the original problem. Okay. The other thing that's always is easy to find, x is just x. A is the specific value of x. So that's why that's there and that's there. And then this guy, he has to be calculated. Oh, my blue, there we go. He has to be calculated. I find him by taking my a and my f of x and putting them together. I don't know why this is being so weird today. All right, here we go. All right, so this guy was f of a. That's when I did that. Okay. If you don't understand how to plug the pieces in, then nothing else is going to matter. So at your seat right now, you got to do like a little check on yourself and say, okay, do you see where I got all that stuff? Do you understand why I put certain things in certain places? Either yes or no, or can you follow how I put the pieces in? The f of x function, the f of a value, the x minus a. Okay. So now what's going to happen next is going to be that I'm going to be able to simplify a little bit in most cases. And so in this case, the 4x minus 5 minus 3, I'll be able to write as 4x minus 8. And here's how you're going to know if you're on the right track. If I try to do the limit right now, and I put a 2 in here, and I put a 2 in here, I get a big fat 0 over 0. And that's what happens every single time we do this kind of limit. The limit definition of the derivative is a 0 over 0 limit every single time. Which is why I had to teach you how to do 0 over 0 limits before we did this. Okay? Because we got to know how to do a 0 over 0 limit. Now, based on your limit quiz, lots of you do know what to do with a 0 over 0 limit. Sometimes you make some mistakes when you do it, but you understood that one of the basic strategies for 0 over 0 limits is factoring. Factoring so that there's a factor you can divide out or cancel out. If I take 4x minus 8 and factor out a 4, which leaves me with x minus 2, then that exact thing happens. I get a factor to divide out. So that's going to leave a 4 in the numerator. It's going to leave a 1 in the denominator because all the factors are gone. The x minus 2 was the only factor down there, and it's divided out. And now we should be able to find a limit. In this particular problem, it's the limit of a whole number. So the limit of a 4 is just 4. So the answer to question 1, the derivative of that particular function, 4x minus 8, or excuse me, 4x minus 5 is the original function. 4x minus 5, what's the derivative when x is 2? The derivative of that function is going to be 4. Oops. We take our formula, We fill in the individual specifics for the problem, the a value that we're given, the f of x value that we're, or f of x expression that we're given, the x. This we have to calculate f of a. If we do it correctly, the result combination should be a numerator denominator that generates a 0 over 0 when you plug in the a value. You should be able to factor and divide out the common factor and then calculate the limit. Okay. Now, I will tell you, if you remember what I said about a derivative is just a slope, this particular function is a line. It has a slope of 4. So the derivative was going to be 4. I knew that before we even started. If you're working with a line, that's always going to happen. Your value of the derivative is just the slope of the line. When we're working with something that's curved, like in problem 2, it's going to be a little different. X squared plus 3x is a parabola, and it's got different slopes at different points along it. If I'm talking about the x squared plus 3x parabola, or any parabola basically, you know, if I'm on this side of the parabola, I would have a negative slope. If I'm on this side of the parabola, I'd have a positive slope. I would have different slopes at different points. I would have a 0 slope kind of at the bottom. So things that are curvy, what makes it curve is the fact that it's got a changing slope. I want you to find, for problem 2, the instantaneous rate of change, which, remember, that is just a synonym, a code phrase for derivative for this particular f function at that particular a. So let's start by seeing if you can find the pieces you need to create the limit. That's our formula every time. The limit of f as x approaches a of f of x minus f of a over x minus a. If you're ready to look at the setup, see if yours is correct, you can look at what I've just written in black for my limit. Now, this is where you have to be honest with me and yourself. If you're looking at that limit expression and thinking, I got no clue where she got that stuff. It's magic. She's just making stuff up and writing it down. I guarantee you I'm not. I am following a certain process. I am looking at certain pieces of this problem and putting things in the formula. If you're not sure what I'm thinking to get these things in the right places, that would be a really good question to ask. If you don't know where that 4 came from, if you don't know why x squared plus 3x is right there, if you don't know why x minus 1 is there, if you don't know why x approaches 1, if you don't know why any of those things are in their places, that's the kind of question you need to ask. Because if you can't write the limit, you're not going to be able to solve the problem, at least not now. So everybody's okay with where everything came from when I set up the problem. Okay. What do you, oh, Selena, go. We don't have to do what? We're not done yet. Yeah. So that's okay. Yeah, so that is actually exactly what we're going to do next. Because if I write the problem out like this, if this is the correct setup for the problem, and I decided I'm going to start figuring out this limit by plugging in a 1, unfortunately, when I plug a 1 in, the numerator is going to come out to be 0, and so is the denominator. And that is not an answer that means anything. 0 over 0 is called an indeterminate form. It's unclear what we're saying. We can't divide by 0 normally. And having a 0 divided by a 0 as attached to a function relationship like this is a little confusing. What we find usually is that means there's a hole there. And a hole can mean that there's still a limit. So I always kind of think about 0 over 0 kind of masks and hides what's happening. It's not an undefined, it's not 0, it's not DNE, it's like, I don't know what's happening. So now we're going to factor. So here we go. One of the things that can help you a little bit is the fact that you are, every time we do one of these special limit problems, these derivative limits, the factor you write in the denominator has to show up as one of your factors in the numerator. So knowing that you have to get x minus 1 up in the numerator might help you get the other piece. Everybody's ability to factor is different, and you might still need to come in and have me just give you a few problems to work on in Excel or whatever on factoring. X squared plus 3x minus 4. One of my factors has to be x minus 1. The other factor to make this problem work would have to be x plus 4. I need factors of -4 that add up to +3. So the magic numbers are 4 and -1. Because this is just an x squared, I can pop them right into the function. Right into the factors. Goes away. Here's what's left. And I finish my limit with substitution. 1 plus 4 over 1. Final answer is 5. You guys get that? Awesome. Awesome. Now, when we learned limits, we did all kinds of different kinds of limits, and then when we took our limit quiz, made it a little challenging. The limit definition of the derivative kind of usually flows the same way. So we'll see a lot of commonality between the problems. Selena, question.
So 5 is the answer.
5 is the answer. What's 4? Okay. I got 1 plus 4 over 1. So that's how I got 5. I took x plus 4 and I plugged 1 in for the x. All right, I want everybody to try number 3. If you haven't started it already, try number 3. Let's see what we can do.